Hi everyone, so this is a video on the applications of partial derivatives. Partial derivatives, they're involved in various sectors. Here we'll just be focusing on the economic side of things. An example of another sector that has partial derivatives involved is in space, where they calculate, use partial derivatives and calculate the orbiting of, well, anything in space. So here are some it's not exactly an fx. It is an fxy here, but sometimes the variables may have some changes, because to suitably represent the elements that are involved in the question. So first we'll be looking at cost function. Cost function is represented as c, and it'll be there'll be a string of variables. It'll be an fxy, but it's just c instead. Previously we've been saying fxy equals then x squared plus y squared plus something like that. While c, it's the exact same thing, it's just that this one became c instead. So c equals so on. Here the cost function, when we differentiate c, it'll be written as this in terms with respect to x and with respect to y. So if we're differentiating in respect to x, we will be getting the marginal cost of x, and this will be marginal cost of y. Alright. So often x and y, the variables here, will represent the products. So maybe there'll be a product A and it'll be represented as x. Well, yeah. So having covered the cost function, now we're looking at the productivity function. So cost is pretty straightforward. Productivity is, there are two variables involved here as well. Instead of having two separate products, in productivity there are labor and capital. Alright, so instead of using x and y, L and K is used instead to suitably represent what is being used in the equation. So it could be, so it's often represented as a P and then a string of L's and K's. Yeah, F, L, and K. So when we're differentiating P, it'll be this. Alright, so when we differentiate with respect to L, it'll be marginal productivity with respect to L. Then same here for K instead, capital, labor. Now we will be looking at an example of the cost function. So for example, the cost function presented here is x to the power of 0.4, y to the power of 0.6. And we are given here that x equals 50 and y equals 100. Yeah, they sort of allocated the number of products that were used here, and then we're going to use this number to find the marginal cost of each of these products. So having gotten the differentiation, then we're just going to sub x and y into these. So we can sort of see that the marginal cost of y is lower than x. If the question asks your opinion, like whether they should make more of y or x, then we could say they could make more of y because it has a lower cost associated with the product. Okay, so the next example we're going to be looking at is the productivity one. Okay, so let's say the function is q, 10k, and L to the power of 0.5. So 10k to the power of 0.5, L to the power of 0.5. So this is the productivity example. So remember, this is labor and this is capital. So first thing we're going to do is to differentiate with respect to each of these variables. Again, this is a product rule. Usually these sort of questions will be given the values of k and l because we're trying to see like whether we should reduce the capital and increase labor, whether they both have to stay the same or increase whichever one. So usually we're given units of capital and labor, and then afterwards we're gonna make an analysis of what we're supposed to be doing with either of these. So here, let's say L equals 27 and K equals 64. So with the n equations, now we're gonna sub it in. So this is dq dl. We're writing the K here. Alright, so now in terms of labor, this is the marginal productivity, and for capital, this is the marginal productivity. Seeing this number, it means that the marginal productivity of labor is more than of the capitals. So that means if we increase the amount spent in labor while keeping the capital constant, the productivity will be higher because it already has the highest productivity. So we've got to put more effort in this rather than the capital. Next, we're going to be looking at maximizing profit. So the purpose, this video is more focused on the productivity and cost functions. It's more focused on these two because the concepts of these two are used frequently in almost any of the questions presented. It's just that here we'll be discussing briefly on maximizing profit. And afterwards, we're going to reach another important part of applications of partial derivatives, which is partial derivatives with constraints. So here, normally for those with constraints, we will introduce the Lagrange multiplier. So that's what the following section of the video will be discussing. So now we're going to be looking at maximizing profit. Alright, so let's say we've got burgers A and burgers B, and their profits are $2, $3 respectively. So we're going to use X to represent burger A, Y to represent burger B, and here is their function. So 10x plus 10y plus xy minus x squared minus y squared. So first we differentiate with respect to x and y. This means that selling 10 burgers A and 10 of B as well would maximize the profit. So in this sort of maximizing profits question is actually a really straightforward one, because this is the simpler type. In certain questions they might give you like revenue. They might give you revenue and cost, and you've got to derive the profit yourself. So yeah, sometimes it's just like that, and it's not as straightforward as this one, because this one we were given the profit. These were the profits. In cases where they don't give the profits, then you will have to make it yourself out of the information they have given you. So yeah, it might not even be two functions, it's just like the function, you will have to make the function yourself. Yeah. So now we're going to be looking at the Lagrange minimizing cost, and then there's constraints here, so we'll be using the Lagrange method as well, the Lagrange multiplier. So if we recall, Lagrange multiplier's formula is so this is the main function, and then this would be the constraint multiplied with this lambda. So the new function would be f, the main function, plus lambda constraint. So the example question is here: a firm makes two goods, X and Y, and due to the government quota, there's a constraint of X plus Y equals 42. And our main function is cxy 8x squared minus xy plus y squared. Okay, so we're gonna make our new function here. So it'll be main function plus lambda, and we've got to make this constraint become like equated to 0. Alright, so this is our new function. Now we're going to be differentiating this function with respect to x, y, and lambda. If there is an extra variable, which we are not going to be seeing here, if for example there's like x, y, z, lambda, like what they're saying up here, so we've got to differentiate with respect to x, y, z, and lambda. So in this case we only have 3 differentiations done, because there's only x, y, and lambda. These are the allocation, the numbers that we get here are the allocations of products in which we can minimize the cost. So that's about it for this video, and questions don't often just stop at these sort of, like, they don't just stop at asking you to calculate outputs, profits, cost, production, so on. Can be anything else, but basically these are the concepts that will prove useful in most questions. Thank you for watching.